Actually, I finished this discussion of two-dimensional vector calculus with a lengthy discussion of Gauss's law in the plane and how that's thought, how we think we should think through that. But we have much to do before we get to that. All right. So this is the flux, and we can calculate the flux for a relatively easy thing. Let's do that before we do anything more. So, example, what am I on? 6? I can't remember. 5. There was a 3. 4, 5. Okay. So here's a vector field I like. F equal to let us say. X over x over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared. This is a nice vector field. Let's find flux. Let's find the flux of F through unit circle. Oh, let's not do unit circle, so boring. Let's do circle radius r. Let's see if we can do that. So you see, we have just figured out that this amounts to calculating the line integral, not of the vector field, right? Of what, though? So first of all, circle of radius r, we do, x equals to r cos t, y equals to r sine t, right? 0 less than or equal to t less than or equal to 2 pi is what I customarily do. If we do that, we got dx is minus r sine t dt, and my dy is r cosine t dt. This is the easiest, I think, way for us to calculate line integrals is with the differential method. Okay, anyway, so the flux, if we do so choose to calculate to the circle of radius r, is going to be equal to the integral of, well, let me just write it out, p dy, right? P dy minus q dx, right? But how's that work out here? This is p, right? And this right here is q, right? So what happens when we plug in the parameterization for p? Yeah, we got our cosine t divided by what's x squared plus y squared for the circle of radius r? Well, it's r squared, the square root of r squared r. We're assuming r is positive, right? So denominator, it'd be r. And the dy, well, we have that up here somewhere. R cosine t dt, yeah, all right, there we go. And then minus the q, which was r sine t divided by r, times my dx, which was what? Over here, minus r sine t dt. Yeah, all right, there we go. Yeah. Oh, look at that. I think we've got cosine squared plus sine squared, people, right? Yeah, we got cosine plus sine squared, so this is actually just integral from 0 to 2 pi of, well, r dt, yeah? One of the r's cancel, but there's another r that remains, yeah? So what's the answer? 2 pi r. The flux is 2 pi r. Does this make sense? What is this vector field we're looking at? So we've got the circle of radius r, right? And the vector field, which I've just had us calculate, is nothing more. R hat. Very good. It is R hat. And so it is pointed exactly in the, I mean, R hat is the n. R hat is the outward pointing normal for my circle of radius r. So this result is entirely unsurprising. The exact dual to this example, I won't work out the details, but if you were to calculate, G equal to theta hat, then the flux through the curve for G would be, the integral over the curve of theta hat dot r hat ds, which would be 0. Because the same circle of radius r, n is r hat, right, for this circle. And of course, if you can envision theta hat, it wraps around tangentially. It's tangent to the, the circle is the integral curve of theta hat, and it never crosses, the integral lines of the theta hat vector field, they never cross the circle, they just lie tangent to it. So never does even one field line of theta hat pierce the circle, so the flux is 0. Which you can also see just because this is 0, so we're integrating 0. All right? Any questions? So what I'm going to prove tomorrow is known as Green's theorem. And so let me write out for you what Green's theorem says. We'll derive it tomorrow. It takes me about a half hour to really properly derive it. But we have time to state the theorem and to use it today. So the statement of Green's theorem is simply this. The integral around the boundary of some region of p dx plus q dy is equal to the double integral over that region of partial q partial x minus partial p partial y dA. This is Green's theorem. And our current project actually is to derive this. Now there's two different ways to look at it. The one involves this flux concept. And that's actually what I'm going to start with. I'm going to give you a proof of Green's theorem as it relates to flux of a vector field. But after the dust settles, this is the go-to formula for Green's theorem. It's the most natural one to use. So why would you want to know about this theorem? Who cares about Green's theorem?
And the first integral, is that a partial r or is that boundary r?
It's the boundary.
Okay, but then these ones are partials.
Wait, we use the same symbol for boundary and partial, yeah.
I just want
Yeah, you're not wrong. So, for example, and again, we're gonna prove this and justify it in the next lecture. The justification takes longer than time I have left today. All right? Yep.
In R in the second integral is the area of the region.
R is a region whose boundary is about partial R. Yeah. So, for instance, if I was to, let me make it more explicit for you. Let's make R the square that goes from 0, 0 to 1, 0 to 1, 1 to 0, 1 back again. All right. So this is R is the interior. The boundary of R is the oriented square path formed by 4 line segments. So if somebody asks you to calculate x squared plus y squared dx plus x cubed plus y cubed dy, over that square, how many integrals are you doing? You're doing 4 separate integrals because you have to parameterize each line segment one at a time. That's annoying. With Green's theorem, we trade this line integral for a corresponding double integral. It then becomes the double integral over R of partial x of q, which in this case is x cubed plus y cubed, minus partial y of p, which in this case is x squared plus y squared by my construction. But that is just the integral from 0 to 1, the integral from 0 to 1 of apparently 3x squared minus 2y dx dy, which we can calculate with ease. Let's see here, my x integral gives me 1 minus 2y dy, which then gives me 1. Oh, come on! Dang it! I didn't want it to work out to 0. It's 0. Wacky. Why is that 0? That's 0. It always works out. I think I got 0. Anyway. I wanted it to be non-zero. Oh, well. So that's what we'll talk about tomorrow.